So welcome back again in the class of microwave filters. I am Zubair Akhtar, your instructor for this class. The topic for today is coupled line filters. So we will see what's the basic mathematics behind these coupled line filters. So in order to analyze the coupled lines, so we have drawn some pictures of the coupled lines. So we have mentioned various currents. So this is port 1, this is port 2, this is port 3, this is port 4. So the current for the port 1 which is going inside is I1. So similarly we have I1, I2, I3 and I4. And individual voltages level at port 1 is V1, say V2, V3 and V4. Now in order to express the even odd modes, so we have drawn the currents. So I1 is I1 plus I2, this is I1. So in even mode, both the currents in the same direction, and similarly on the odd mode. So this is in order to represent the even mode impedance of this line. So this is called ZOE. This is Z0 in even mode and this is Z0 in odd mode. So in order to represent a voltage at any point in like transmission line, these are like VA for this line and VB for the top line. Okay. So this is the configuration for the similar configuration for the third and fourth port. Now we are analyzing a special case of coupled line filter where terminal 2 and terminal 4 are open circuited. So this is the condition when we are getting a kind of band pass transfer function from these coupled line filters. So this is the special case and we have chosen this as open circuited. Okay, and let's assume the transmission line starts at L equals to 0 and it is of length L and we are moving in the positive Z direction. Okay, so let's write down what are the currents here. So if we want to say what is I1, so I1 is I1 plus I2. So we are just defining this in terms of small I1 and I2. So similarly other currents we need to define. What is I2? So I2, you can see here I2, it is I1 minus I2. So I1 minus I2. Similarly I3. So if we focus on I3, this is the I3. I3 is I3 minus I4. Okay, and if we want to define I4 as well in terms of the even odd currents, so I4 would be I3 plus I4. Okay. Now it's very important to know about the special configuration. So we are working in this configuration where this terminal is open circuited, say and if we would like to see the input impedance of this transmission line, while this is open circuited and we are assuming the whole system is excited in an even mode. So the characteristic impedance for that case would be for this line is Z even. So if we want to write the input impedance for a special case, this Z input, okay, at any instant L. So this is the L, so in terms of L, so it would have a form of Z cot of beta into L. So this is very standard expression. So we have seen in our previous classes, so Z in L is equals to minus J ZOE into cot of beta L. Sorry, this is cot. Okay. Cot of beta L. Now, if we want to analyze this little bit more in terms of voltages, if we want to write a voltage, say voltage at this line VA, okay, Z, okay, VAZ, if we want to say line 1, it would be same as VBZ. Why? because we are saying these two are in common mode. Common mode means they are having same excitation and the voltage are in the same manner they are varying on the transmission line. So the voltage which is like on a point here, it's gonna be the same as voltage at position Z at a different line. Okay, so what it could be, we can say in terms of say V1. So this is Vz. So V in even mode, positive Z. So this would be e to the power minus j beta z minus beta L and plus e to the power j beta z minus L. Okay. So if we solve this, if we divide by 2 and multiply it by 2, so this gonna be equated as this becomes a cos of beta L minus Z. Okay. So this is our Z in L. And if we wanted to say in terms of say this is the voltage, sorry, this is not Z in, this is our voltage VA Z. Okay. So now if we wanted to say the Z in, which is this is called beta, this could be also written as this voltage in terms of this Z in, it gonna be equals to I1 into Z in L. Okay. So this gonna be written as I in, this is the current into impedance. So if we are talking about impedance at this point, so this is gonna be Z equals to 0, okay, and this is the voltage at that moment, and then we have a multiplication with the input impedance at that point. So this is gonna be voltage on this line. Okay, now similarly with the kind of odd mode, if we say, so Z in at L for odd mode, this is gonna be J Z O cot of beta into L. Okay. However, in odd mode, what gonna happen? This VAZ gonna be opposite to of VB Z, and this gonna be equals to VE e to the power minus j beta Z minus L plus e to the power j beta Z minus L. Okay. If we solve this, so this again gonna be equals to twice of VO, because this is odd mode, so we can say this is odd mode, and this is going to be also equals to cos of beta L minus Z. Okay, so this is the, and if we want to say on the second line, so we need to add a negative sign to it. Okay, so these are the voltages. Now we can also define this voltage in terms of current. So this is gonna be equals to I2 Z in. Okay. So after we are getting like a VA and VB values for even and odd mode, so now we can define a complete voltage, how we can get a complete total voltage at port 1. So total voltage at port 1, it's gonna be equals to V1, this is gonna be VA at 0 dash plus VA at 2 at 0 plus VA at 3 at 0 plus VA 4 plus. So this is the overall voltage V1. So this is like for all cases VA for port 1, port 2, port 3, port 4. So now by putting these all values, we can calculate the total voltage. So we can write this whole equation in expanded form like this: even mode I1 plus Z, odd mode I2 cot of theta minus J Z of even mode I3 plus Z of odd mode I4 cosec of theta. Okay, where theta is equals to beta into L. So this is our V1. Okay, now we know that these I1, I2, I3 and I4, they are defined in terms of capital I1 and I2. If we try to calculate what is the I1 from here, so we can say I1 is going to be, if we add these two, I1 plus I2 divided by 2. Okay, what would be the I2 here? I2, if we subtract, okay, so it's gonna be 1 by 2 I1 minus I2 minus I2. Similarly, I3, if we say I3, it's gonna be 1 by 2. Okay, so if I say I3, it's gonna be capital I3 minus I4, and I4 gonna be 1 by 2 I3 plus I4. If we put these values of small I1, I2 here, and we'll get the overall expression in terms of capital I1 and capital V1. Okay, so if we put these values, so this expression gonna be, the simplified expression of this gonna be equals to Z naught, say J, Z naught even capital I1 plus ZOO, ZOE I2 plus I2, then ZOO I1 minus ZOE I2, and this whole expression is getting multiplied with cot of theta. And there is another expression, this is J by 2 minus J by 2 ZOE I3 plus ZOE I4 plus ZOO I4 plus minus ZOO I3, and this whole expression is multiplied with cosec of theta. Okay, so this equation is very important. However, you can simplify this by putting this and you will get this expression. So this equation is why this is very important. You see, like, this is relating you with the V1, capital I1, I2. So this is basically a equation which is of this form. Okay. So you are basically getting a Z parameter out of it. If in terms of matrix we will write, this would be something like this. Okay. So now if we know this and we know the symmetry, so we can write all the Z parameters from this. So what are the Z parameters for by seeing this, say Z11, Z22, Z33, Z44. How they gonna look like? So Z11 gonna be V1 upon I1. So this gonna be J Z0 by 2. So what gonna be? This term is I1, this term is I1, and this is this caught here. So what it gonna be? Z O E plus Z O O into cot of theta. Okay. Similarly, if we want to write, say, Z12, so Z12, this is going to be equals to Z21, and what are the 3, 1, 3, 4 and 4, 3? They are having the same relations. So this is going to be J by 2. What is Z12? So this is 2, this is 2. So let's write down Z O E minus Z O E. So this is Z O O, I guess. If it is not, yeah, it is Z O O. So this is Z O E, Z O O into cot of theta. What are the other parameter we can define? Z13, Z31 and Z24 and Z42. So if we write by seeing this equation, so this is going to be minus Z by 2 for sure, then 3. So this is Z O E, and where is I3 again? Here, minus Z O O into cosec of theta, and the final parameter, which is Z14 equals to Z41 is equals to Z23, Z32. How we can calculate this? So 1 with 4. So minus J by 2. So what is the coefficient for the I4 here? ZOE minus plus ZOO cosec of theta. So these are the very important results if we want to design a coupled line filter. Okay, so we need to remember these results, and so now we need to analyze the same structure with the given values of the Z parameters, the obtained values of Z parameter. So if we want to design a, say, filter, so through image impedance parameter method, so we need to calculate few other parameters with the help of these Z parameters. So we know Z parameters. So what would be the input image impedance for this case? So we know the formula, so we can write directly the formula for this: Z11 square minus Z11 Z13 square divided by Z33. Okay, if we put these values here and if we solve this expression gonna be something look like, so it's ZOE minus ZOO whole square cosec square theta. Similarly, the other expression for ZOE plus ZOO cot square theta. Okay, so this is the image impedance. So for simplicity, we have chosen this line to be as length of lambda by 4, which is theta comes out to be pi by 2. So for this, if we try to see and we simplify this, so cosec pi by 2, and if we put the cot pi by 2, so this gonna be simplify image impedance is ZOE minus ZOO. So this gonna be very simplified relation out of this, and 1 by 2. This is 1 by 2 is coming out of this expression also. So if we simplify, you will have 1 by 2 here. So 1 by 2 like this. So it is very important to observe here that, so because of this some cancellations, we have this square root and there is square. So this, if this expression is negative within the square root, so it cannot give us a real value. So this expression is only valid for giving a real value when ZOE is greater than ZOO. So this is saying that image impedance is real for the given theta value. So if we say go little bit in that side, so it gonna become imaginary or something like that. So this is the condition for getting a band pass filter, like the pass band is like image impedance is real, so we have a pass band here. Okay, so now we'll try to calculate the propagation constant. So with image impedance parameter, we know that what's the propagation constant. We know the expression of the propagation constant. So we'll calculate the propagation constant for this filter. So the propagation constant, cos of beta, is defined as an image impedance method. We have given a proof of this earlier. So is this. So due to the symmetry, we can write this like, so there is no square root, so we can directly write the cos of beta is equals to Z11 divided by Z13. Okay. So Z11 is equals to Z33, so it's coming out, and this is the way we can write. So if we say, if we want to put these values, say Z11, what is this? This is Z11, and what is Z13? Z13 is this. So if we take divide of these, so what we are getting? So we will get ZOE plus ZOO divided by ZOE minus ZOO multiplication of cos of theta. So now we have cos of beta. Okay, so now it's these are the basic equations to design. So now we have the propagation constant, and now we have all the impedance parameters, and we have the image impedance. So now we can design such type of filters using image impedance method. So these are the basic design equations that we're gonna use in the next design example, where we're gonna design a filter with these expressions.